All right, so get this. What if I told you that you could, like, mathematically speaking, cut up an apple and then reassemble the pieces into two, like two whole apples?
Whoa, that sounds impossible.
Right. It totally defies, like, everything we know about how things work. But that's exactly what we're going to be talking about today. The Sierpinski-Mazurkiewicz
The
Paradox.
Sierpinski-Mazurkiewicz Paradox.
Yeah, so it's this wild concept in set theory that basically plays with the idea of infinity. And honestly, it's going to kind of twist your brain a little bit.
I can imagine.
Yeah, so think of it as like the famous Banach Paradox is like kind of quirky cousin, but instead of messing around with 3D space, this one stays on a flat plane.
Oh, okay. I see.
Yeah, and before you get any ideas about, multiplying your snacks, we need to be super clear here. This isn't about actual, like, physically duplicating stuff. This is about this super bizarre world of mathematical sets where infinity just kind of throws a wrench into everything we think we know about area and size.
It's amazing how our everyday experience can clash with the abstract world of mathematics.
Oh, totally, totally. And that's what makes this whole deep dive so fascinating, right?
Dear.
So to start unpacking this paradox, like, we need to understand this concept called piecewise congruence.
Piecewise congruence.
Yeah, so imagine you have two jigsaw puzzles. You can take the pieces of one and, like, rearrange them, and boom, you get the other. That's piecewise congruence in a nutshell. Cutting a shape into pieces and then putting those pieces back together in a different way to form another shape.
It's like a geometric transformation puzzle.
Yeah, exactly.
Where the pieces themselves stay the same, but like their arrangement is just different.
Yes,
Oh.
precisely. But here's where things get strange, okay? Normally, we expect shapes that are piecewise congruent to, like, have the same area.
Right. Yeah.
Like, if you cut up a square and rearrange the pieces into a triangle, the area should stay the same.
Right.
Makes sense.
Right. That's just how area works. Right.
But the Sierpinski-Mazurkiewicz paradox just throws that expectation right out the window. It shows that in the realm of infinite sets, a set can be piecewise congruent to two copies of itself. It's like taking a pizza, cutting it up in a really specific way, and then, like, through some clever rearrangement, you end up with two pizzas the exact same size.
That's so strange. Intuitively, it just feels like that can't be possible. Like, you can't create something from nothing.
Exactly. Our intuition screams, that's impossible. But in the world of infinite sets, things are they're just different, right? Our normal rules about measurement and size, they just don't apply in the same way. So how does this mind-bending paradox actually work? What's going on behind the scenes, mathematically speaking?
Well, it all comes down to a couple of key concepts: free semigroups and isometries.
Okay.
I know. Those words might sound a little intimidating, but just bear with me for a second.
They sound like something out of a textbook. Right, exactly. But let's break them down. Let's start with free semigroups. Think of them as a set of instructions for, like, moving things around. Each instruction is like a basic move,
Oh.
like rotating a shape or shifting it to the side.
So it's kind of like a recipe for manipulating shapes.
Oh, perfect analogy, yes. So now let's add in the isometries. These are specific types of movements, in this case, rotations and translations of a flat plane. And here's the key. These isometries are chosen really carefully so they don't, like, undo each other.
What do you mean?
For instance, you might rotate by an amount that's not, like, a simple fraction of pi.
Okay.
It's about making sure the movements are independent and they don't lead back to the start in a simple way. So picture this. You pick a point on the plane and apply these special instructions, the rotations and translations, over and over and over again. What you get is an infinite set of points. And that set has a special name. It's called an orbit.
Ah, I see. So you're tracing the path of that point as it moves across the plane.
Yes, exactly. And here comes the truly paradoxical part. You can actually split this orbit set into two parts. Let's call them part A and part B.
Okay.
And then, using our special isometries, we can rearrange each part to recreate the entire original set.
Wow.
So part A can be transformed into the whole orbit. And get this, part B can also be transformed into the whole orbit.
Wow.
It's like each part contains, like, a blueprint for the whole, right? And this is where our understanding of how parts and wholes should relate, it just kind of, it falls apart.
It's like you're taking half a bag of marbles, and you can turn each half back into a full bag of marbles.
Right. And that's where we have to step back and realize that, our everyday intuition about size and parts, it completely breaks down when we're dealing with these infinite sets. They just behave differently.
Our intuition just isn't built for infinity.
Right, exactly. It's like the Sierpinski-Mazurkiewicz Paradox is this, it's like this siren song luring us into this strange and wonderful world of infinity where things just don't behave the way we expect them to. But there's another piece to this puzzle that we need to look at. The axiom of choice.
Oh, okay.
And this is where things get even more fascinating.
So the axiom of choice, it's basically like saying if you have, an infinite number of sets, you can always choose one thing from each set, even if there's no, clear rule or pattern for how to choose.
Choices, right? Sounds simple enough. But how does something that seems so basic lead to, all these mind-blowing consequences, especially with infinite sets?
Yeah, it's like a tiny ingredient that just totally changes the whole recipe,
Okay, so break it down for me. What exactly does this axiom of choice, actually say?
Okay, so it says, basically, if you have an infinite collection of sets, right, you can choose one element from each set, even if, there's no rule for how to make those choices.
So it's like having, an infinite number of bags of marbles, and each bag has, different colors, and you're able to just pick one marble from each bag, even though you don't know anything about what's inside.
Yeah, exactly.
That-
The cosmic grab bag, but with infinity.
Infinite grab bag. I love it.
Yeah.
Okay, so that makes sense. But why does this cause so much controversy in the math world?
Well, you see, it can lead to some, really weird conclusions. Like, for example, this Sierpinski-Mazurkiewicz paradox we're talking about, right?
Right.
The axiom is basically what lets us do these crazy decompositions and rearrangements of infinite sets. It's like it gives us this loophole,
So we can bend the rules of, measurement and size when we're dealing with infinity.
You could say that, yeah. It's just some mathematicians think it's a bit too powerful. It leads to results that they just don't feel right,
Yeah, but isn't that what's so cool about math? It pushes us to question everything we thought we knew and see what's actually possible.
I mean, you're not wrong.
So the Sierpinski-Mazurkiewicz paradox, it's made possible by this axiom of choice.
Yeah.
But we're not breaking the laws of physics or anything, right? We're not actually creating something out of nothing.
Exactly. It's more about, showing the limits of how we understand measure, like concepts like area and volume.
It's like our everyday tools for measuring things, they're not enough when we step into this world of infinite sets.
Exactly. Our normal rules, they don't work the same way in infinity.
So it's not that, the math is wrong. It's more like our way of thinking about measurement needs to, catch up.
Right, exactly. The Sierpinski-Mazurkiewicz paradox shows us that infinity is just, well, it's full of surprises. It's a different world.
It's a trip, that's for sure.
Yeah.
But let's bring it back down to earth for a second.
Yes.
Some of our listeners might be thinking, okay, this is all very cool and trippy, but what's the point? Does this paradox actually affect anything in the real world?
That's a great question. And it's true that the Sierpinski-Mazurkiewicz paradox might not have direct applications in our everyday life. But it's got these huge implications for how we understand math itself.
So a test for our math theories, right?
Exactly. It's like
Yeah.
we're pushing them to their limits.
And by doing that,
Yeah.
we see where those theories are strong and where they need some work, right?
Absolutely. By exploring these paradoxes, we gain a deeper understanding of the foundation of mathematics and what infinity actually means.
It's like peeking behind the curtain, right?
Yeah, exactly. We see how it all works, the underlying principles,
I like that. So it's not just about the end result, it's about the process of getting there, right?
Right.
The journey.
Exactly. It's a journey, a challenge. It helps us think more abstractly.
And who knows, maybe someday this super abstract exploration will lead to breakthroughs in other areas. I mean, history is full of examples where a math concept seemed totally useless and then bam,
Yeah.
changes the world.
You never know, right? That's the cool thing about knowledge. It's unpredictable.
Absolutely.
Oh.
Okay, let's take a moment to recap what we've covered so far. We've been talking about this Sierpinski-Mazurkiewicz paradox, which shows us that a set can be divided up in this crazy way where each part can make a copy of the whole original set.
Right.
We've talked about piecewise congruence, where you cut a shape up and rearrange the pieces to make a new shape. We talked about the axiom of choice, which lets us make choices from an infinite number of sets, even without any clear rules for how to do that. And now we're about to go even deeper into this rabbit hole and explore this concept of non-measurable sets.
Okay, so non-measurable sets. These are sets that are they're so strange that we can't give them a size or area using, our usual methods of measurement.
Like trying to measure a cloud, its shape is always changing, so you can't get an accurate measurement.
Right.
Perfect analogy. That's exactly it. Non-measurable sets are like mathematical clouds. They're so complex, their boundaries are just fuzzy, and we can't pin them down with our normal measuring tools. But before we go head first into that, let's take a little detour and see how all this connects to some bigger ideas in mathematics.
A detour. Now you've got me intrigued. Where are we headed?
So, these non-measurable sets, right? We've been kind of circling around them this whole time.
Yeah, they sound, I don't know, kind of spooky.
They're definitely strange, They exist in a way that makes it impossible to measure them like we normally would.
Okay, so to unpack that a little bit, what makes these sets so elusive? Like, why can't we just, get our mathematical rulers out and measure them?
It all comes down to structure. Remember those free semi-groups we were talking about earlier? The sets of instructions for, like, moving points around on a plane.
Yeah, the ones that were so key to creating that whole paradoxical set in the first place.
Exactly. Those sets, those orbits that the free semigroup creates, they're so deeply intertwined with the structure of those non-amenable groups,
Okay, yeah, I'm following.
And because of that, they kind of slip through the cracks of our normal ways of measuring. They defy our usual tools.
So it's not like they're, like, empty or anything, right?
Yeah.
It's more like they exist in a way that's just, like, fundamentally incompatible with how we normally think about size and measurement.
Exactly. It's like they exist in a higher dimension of complexity, a dimension where our regular tools they can't reach.
Okay, that's a pretty wild thought. It's like trying to, I don't know, like, grasp a concept that's just beyond human understanding, you know what I mean?
It's a bit like that, yeah. This Sierpinski-Mazurkiewicz paradox, with these non-measurable sets at the heart of it, it really shows the limits of our intuition. And it shows how infinity can really challenge our understanding of how things work.
So if we can't really measure these sets in the usual way, does that mean they're just, like, mathematical curiosities? Like, are they just these weird things that exist but don't really have any use or significance?
That's a good question. And while they might seem like oddities at first glance, non-measurable sets they're really important for how we understand math today, especially in areas like measure theory and set theory. They make us really question what it means to measure something, And they force us to come up better, more sophisticated tools for dealing with infinity.
It's like they're pushing us to, like, expand our mathematical horizons, right?
Exactly. They're a testament to the power of abstract thought and the endless creativity of mathematics. And speaking of pushing boundaries, you remember we touched on the Banach-Tarski paradox earlier.
Oh, yeah, you mentioned it was like the Sierpinski-Mazurkiewicz paradox, but, like, on steroids or something?
That's where things get even crazier,
Okay, I'm ready for another dose of mind-blowing math. Hit me with it.
All right, so the Banach-Tarski paradox, it takes this whole idea of paradoxical decomposition to a whole other level. Imagine taking a solid sphere, like a billiard ball,
Okay.
and cutting it up into a finite number of pieces. But these pieces they're very specific, very strange shapes.
I'm picturing, like, some seriously complex shapes, like almost fractal-like or something.
Yeah, you're on the right track. So now here comes the really mind-blowing part. Using only rigid motions, which means like rotations and translations, you can take those pieces and reassemble them into two solid spheres.
Hold on. You're saying you can take one billiard ball, cut it up, move the pieces around, and boom, you have two billiard balls. That sounds like magic, straight up.
It does, doesn't it? But it's a real mathematical theorem. And just like the Sierpinski-Mazurkiewicz paradox, it all hinges on these non-measurable sets. They're the secret sauce that makes this seemingly impossible thing possible.
So we're not, like, creating matter out of nothing, right? We're just kind of rearranging what's already there, but in a way that just seems to defy logic.
Precisely. The Banach-Tarski paradox shows just how much our understanding of volume and measurement can break down when we try to apply it to infinity, It really challenges our basic assumptions about how the world works.
It's a good reminder that there's so much in math that we still don't know, so much left to explore.
Absolutely. And who knows what other crazy discoveries are waiting for us out there.
Well, I think we've given our listeners plenty to think about today. We've gone from duplicating a plane to doubling a sphere, and it's all thanks to these bizarre infinite sets and these mind-bending non-measurable sets.
It's been a wild ride for sure, exploring these concepts that really challenge how we think about things.
So the next time someone tells you the math is boring, hit them with the Sierpinski-Mazurkiewicz Paradox or the Banach-Tarski Paradox. I guarantee you it'll be a conversation starter.
It'll definitely get them thinking, that's for sure.
That's a great point to end on. Thanks for joining us for this deep dive into the Sierpinski-Mazurkiewicz paradox. Until next time, keep those brains buzzing.